This film illustrates how our department works with climate and effects of climate change on different timescales and for different periods of time in Earth's history. We will be looking at things that occurred millions of years ago, some thousands of years ago, what is going on at present time, and what may happen in future scenarios. Further, we would like to show and illustrate how we work across different disciplines with data acquisition in the field, with laboratory experiments, and with modeling. Enjoy the film.
My research focus is Mesozoic stratigraphy and paleoclimatology using calcareous nanofossils, geochemistry and essentially stable isotopes, and cyclostratigraphy. And I would say that the way it has evolved in recent years is that people are using more and more these different disciplines to do integrated stratigraphy to build the best possible edge models. And also that nowadays we have achieved a very, very high precision in radiometric dating, which is making it really interesting to compare with results from cyclostratigraphy. With a number of contributions to build a much better geologic timescale for the maceration stage, which is the last stage of the Cretaceous, on paleoclimatic changes during that stage.
I study how the coasts change in a changing climate. I do that both in a short time perspective and a longer time perspective. In the longer time perspective, we're interested in reconstructing Holocene relative sea level changes, as these tell us something about how the Greenland ice sheet affects the global sea level as well as the vertical land movements. We use coastal morphological features such as beach ridges and their internal archives to investigate sea level variations. And we use geophysical methods such as ground-penetrating radar in combination with dating methods to establish these sea level curves. We show that the coast of Greenland respond to a warming climate the exact opposite way as the rest of the Arctic does. We show that the deltas of Greenland are growing, which is contrary to the general trend of an eroding Arctic.
I use satellite remote sensing data to understand changes in vegetation resources at the global scale. Remote sensing data allows us to go 30, 40 years back in time to understand the changes that we have seen over these 30, 40 years. Surprisingly, we learned from such data that the global drylands have actually become substantially greener over this period. Normally, we would expect a coupling between climate change and desertification, something like deserts become bigger and spread over time, but this is actually not the case. And we are now trying to understand what are the implications for the 1/3 of the global population living in global drylands. We are now trying to figure out whether this increased greening is actually for the better or the worse.
Here at the Center for Permafrost, we are focusing on how ecosystems will respond to climate changes across Greenlandic sites. We have been looking at permafrost samples. Here we see a surprising high content of nitrogen, and we see a rapid turnover of the carbon in the permafrost upon thawing. We're also focusing on the net effect in terms of fluxes of greenhouse gases from the surface. We're measuring it, both methane, CO2, N2O. Interestingly, we see a net methane uptake, and when we do area integration for North Greenland, we see a net uptake. If you compare the permafrost to the vegetations, we also see that below ground carbon from the roots is surprisingly important. We see again a fast response to climate changes. For instance, we see that when we are having warming experiment in the field, roots are growing more and being longer, meaning that they can get access to the nutrients possible release from permafrost. We're not doing it only in Greenland, we also do it other places. We're doing it in Svalbard, Sweden and in Denmark. There has been a project Climate since 2005 where heat sites have been manipulated with increasing CO2 concentration, warming and drought. And that is a very important component not only in Denmark but also Greenland. They're not only warming, but maybe even more important, the future of water balance is to control how ecosystems will functioning and behave with climate changes.
Our research group is interested in predicting the hydrological impacts of climate change towards the end of this century. For this purpose, we are using the output from climate models, which we are then feeding into our hydrological models. Before doing so, we need to do bias correction because there are systematic errors and bias in the climate models. Our hydrological model can give estimates of evapotranspiration, stream flow, groundwater recharge, and irrigation requirement. Our results have shown that we are probably facing higher stream discharge during wintertime, less discharge during summertime. I want to emphasize that these results are subject to a number of uncertainties. One major uncertainty is related to the uncertainty of the climate model predictions.